Okay, so we are currently looking at this next part. This is going to be our 6.5 notes for today. So we have two theorems at the very beginning. We have 6.1 perpendicular bisector theorem. And for this theorem, I want us to look at three particular things. And we're going to look at our if-then statement. If line CP is the perpendicular, we're going to underline that, bisector, get another color if you have one, and change it, I don't know, to blue, for instance. Oh, it didn't change. Change to blue. There we go. Of AB. And then our then statement says this last part of CA equals CB. And now there's a particular reason why we do it like this. We want to know exactly what these three pieces of information mean. Well, we know that perpendicular means to be 90 degrees. Okay. And so if we look at our diagram, we're going to see that there is such an angle that is 90 degrees. In addition to that, we do have, oh, change again. We do have a bisector. Let's remind ourselves that in a bisector, we need a midpoint. Our point P here is our midpoint of the segment AB. And we are knowing this because of these two congruent segments, AP and PB. So, remind ourselves, two congruent pieces. And the last part is we're looking for that CA equals CB. If the first two parts are true, if we have that bisector, that perpendicular bisector, so 90 degrees and two congruent pieces, we can say that CA and CB are going to be congruent. Or in other words, they're going to be equal to each other in value. So to really break this down, I want us to think about it as if we have these pieces of criteria. Here we need a 90-degree angle. Oh, that didn't change color. 90-degree angle. Then we need that bisector. And the last piece of information that we need is those two congruent sides. Now I can see where there could be a little bit of confusion with that bisector and congruent sides, but let's remind ourselves that bisector is a more specific kind of congruent sides. Okay, bisector means it's part of the same line and it has two congruent pieces within that segment. So just making sure that we are understanding that difference here. Well, we're going to take the exact same approach with the next theorem. Except with the next theorem, it's actually going to be a little bit easier for us because we already know some of the information. We know that dA equals dB. That's illustrated right here. And if dA equals dB, then there exists such a line that we have a perpendicular part and the bisector part. So here is our perpendicular. Then here is our bisector. And what you'll see here is that we started with our congruent sides. And we ended up getting our 90-degree angle. And we got our bisector. And that's the most important part of the first two theorems. Now, looking at these two examples here, if you are actually part of the class got a super good explanation as to finding and rationalizing all the information. And so in doing so, I think it's really good for us to understand how we really find these answers. So if we're looking at the first example here, example 1A, we're looking for the measurement of RS. Well, if we know our theorems very well, we would pretty much automatically assume this has got to be 6.8. And for those people who assume that, you'd be correct. RS does equal 6.8, but I want us to make sure that we know exactly why. And so the way that we're going to rationalize this is we're going to look at this problem and we're going to see what the actual diagram is going to give us. So if we look at the diagram, we have two congruent sides that are part of the same segment in RP. So that is our bisector. In addition, we have this 90-degree angle, which indicates that we are perpendicular. So we have 90 degrees. And the only thing that we're missing is that third piece, the congruent side. Just like so. But because we knew we had a perpendicular bisector, that's how we know that those two sides are congruent. And so what I would write here, if I were to write this into a sentence, is since SQ, the line SQ, I should say, is the perpendicular bisector, and you can kind of shorthand it a little bit, bisector of segment PR, it follows that SP is equal to SR. So if we look back at the if-then statement from our problem here, it shows, again, if CP is the perpendicular bisector of segment AB, then CA equals CB. Well, that's exactly what we're doing here. We're saying that a line is the perpendicular bisector of a segment. Then we're saying that because that makes sense, because that's true, therefore the two sides between that one point and the two original endpoints are equal. The distance between those two are equal. I won't fully go over every single rationalization, but I will go over some that I think would make a little bit more sense and need a little bit more clarification. And so we move on, we go to B, and we're still going to be able to try to figure out what information it's telling us. And so if I come in here with a color here, I know I see 24 and 24 immediately. That's what we have as our congruent sides. And so we have our congruent sides. We also have our 90-degree angle. And then we followed it up with, we're missing our bisector. And so the difference between the first problem we did and the second problem we're doing now is that the second problem is using a different theorem than the first one. Now, those of us who are paying attention, we would say that the first problem we did was theorem 6.1, and you'd be correct. That is theorem 6.1. B, however, is 6.2. So in this case, we're finding our bisector. And in this case, we know what needs to be done. If we have a bisector, we know that those two parts are congruent. Therefore, EF must be 9.5. But make sure you're paying attention. It says EG, not EF. And so the way we're doing that one, EG equals EF plus FG. EG equals 9.5 plus 9.5. Therefore, EG must equal 19. And that's that problem. Next problem. This is eerily similar to part A. Recognize we have our bisector. We have our 90 degrees. Oops. And we're looking for those two congruent sides. Okay. But because we have that bisector, that perpendicular bisector, we can then say that these two sides must be congruent to each other. And because they are expressions, we have to put them equal to each other to be able to figure out what they actually, or what the actual values are. So first we're going to solve for x. Subtract 3 on both sides. We get 2x equals 14. X equals 7 once you divide by 2 on both sides. Again, careful, make sure you're putting in the right answer. We're looking for AD, not looking for X. AD is 5 times 7. AD is 35. At this point, if you had missed the lesson, I'd go ahead and pause right now and try to do these three on your own. Give you a moment for that. And of course, this is a recording, so I can't quite just stop and wait as if you were really with me. We are kind of asynchronous here. But I'll go ahead and give you these answers. CD is going to be 27. PR is going to be 10. And then GH, you should have an X value of 8, and then have a GH value of 16. Okay, so as long as you get those answers, you should be good. Again, I would try to rationalize your answers as best you can, especially going forwards and backwards using the regular perpendicular bisector theorem and the converse of that theorem. Okay, moving right along. If you have this blurb in front of you, I think it's a good thing to read on your own time, but I'm not going to do it for this time's sake. But I am going to look at these two theorems here. And what we should see here is that these theorems are very similar to the previous two theorems, in that we're going to kind of color coordinate everything again. First, we're going to read it. If ray AD bisects angle BAC and segment DB is perpendicular with ray AB and segment DC is perpendicular with ray AC, then DB equals DC. And that is a mouthful, a lot of math jargon just spoken right there. So color coordinate, I'm going to color this part here. AD bisects angle BAC. Well, this is angle BAC. And this, what's just circled right now, is what we're referencing. Because we know those two angles are congruent, that's what that semicircle kind of curve looking thing means. Because that's the case, we know that those are congruent. Then, or rather, I'm going to write that down. So bisector. And if you want to be more specific, you can say angle bisector. Then it says that we have some perpendicular figures here. And what's circled in blue is our perpendicular figures. We'll still have that 90 degrees from the previous two theorems. And the last part, we'll see that we have DB equals DC, and that is these two segments right here. We're basically just saying that those two are congruent only if we have the first two criteria, the angle bisector and the 90 degrees here. So again, we're going to have our congruent sides. So the only main difference between these two is what kind of bisector we're working with. Of course, what we're working with right now is the angle bisector, and what we were working with previously was the segment bisector. So making sure that we can make sure of that distinguish or making sure that we can see that distinguish. Okay. Now with the converse, we're working a little bit backwards. DB and DC indicated by these two congruent pieces. And we'll have those congruent sides as part of our if statement. Then we have our second piece here. We have our 90-degree angles here, like so. And just like the previous theorem we just learned, we're going to label every single piece. We know that these two are congruent right there. Just as how we have said before. Overall, these are pretty easy. Should be pretty easy at least. Move on. We look at these two problems here, A and B. And we look and we see that JH and JG are going to be congruent to each other. So definitely would circle that. Those two are the exact same value. Therefore, we have congruent sides. Then we have those two 90-degree angles, those pesky right angles there. And what we're ending up with is what we're looking for is 42 degrees. Or sorry, rather, we were looking for those angle bisectors, and I kind of just gave the answer out already. But we're looking for the angle bisector of angle GFH. Well, if we know that we have congruent sides and those 90-degree angles, we can therefore say that there exists an angle bisector such that angle GFJ and angle JFH are congruent to each other. And so now we've found our angle bisector. Once we found our angle bisector, we can therefore say that the measurement of angle GFJ is 42 degrees. Now, if we think back to the theorems, this theorem uses 6.4, which feels a little odd, going a little bit out of order. But this theorem is 6.4. The reason why is we're looking for the angle bisector and not starting with it. And so kind of the way I would rationalize this is in a kind of roundabout way is I would say since JH equals JG and both angle G and angle H are 90 degrees, it follows that ray FJ is an angle bisector to angle GFH. Again, this is not terribly difficult. You probably could have done this problem immediately and said 42 degrees. But what I want us to really think about is how can we think critically and think deeply within our brains to be able to explain an answer. Because again, what I'm doing here in this sentence is I'm basically reiterating what the proof said or what the theorem said. I have both parts. I have the equal segments and I have the 290 degrees, even though I didn't write it necessarily the exact same because that's a lot of writing and a lot to say, at least verbally. I did basically say it. Now, would this be acceptable in a proof? Maybe not, especially when you get into upper level, but this is high school geometry. I really don't think anybody's going to hark on you saying angle H is 90 degrees because, well, all of those angle H's would be 90 degrees if that was an intersection. So I think it's safe to say that we can say it like this. So if this was 6.4, we definitely need an example of 6.3, and we do see it here in this B. This is definitely a 6.3 problem. That reason being is, well, we have our bisector already available right there. Then we have our, write that down first, bisector, angle bisector more specifically. And we have those 90-degree angles. And the only thing that we're missing here are those congruent sides. But just like what theorem 6.3 says, is that if we have that angle bisector and those 90-degree angles, we know for sure those two segments are congruent. Because they're congruent, put them equal to each other. Solve for x, like so. Get an x value of 5. But remember, this is not our answer. We're looking for RS. RS is going to be 6x minus 5. Replace the x with a 5 minus 5. And you simplify that down, you get 25. We recognize that 6 minus 5 is, although it doesn't seem like it, it is technically more difficult than just PS, which is 5x. Recognize that they are both the exact same, and because they're the exact same, we could have just done 5x. 5 times 5 is still 25. Could have done it like that. And that's that answer. Again, take some time, stop, try to do these on your own. But I will go ahead and give you these answers. That the measurement of angle ABC is 112 degrees. Oh, I messed that up a little bit. That's okay. I think I reclaimed myself there. And JM is going to equal 24. We have example 3 here. And example 3 wants us to write an equation with the perpendicular bisector, remind ourselves 90 degrees, and two congruent pieces, with endpoints P and Q at -2, 3, and 4, 1, respectively. So go ahead and mark that in. That's P. This is Q. Connect them. And we're looking for the perpendicular bisectors, more specifically the equation of the perpendicular bisector. But in order for us to make an equation for the perpendicular bisector, we need to figure out what the actual values we need to look for. And the first value I would look for, specifically with the bisector part of this, is I need a midpoint. The bisector needs a midpoint to make sense. But then perpendicular, we need to find the slope in order to make this make sense. So we're going to do it in that order. We're going to find midpoint. And then we're going to find slope. We have a little bit of a twist with that slope in just a second. With midpoint, of course, we have the midpoint formula, x1 plus x2 divided by 2, y1 plus y2 over 2. Plug in the values that we have. We're going to get -2 plus 4 over 2 and 3 plus 1 over 2. We simplify that down. We're going to get 1, 2. And we'll go ahead and mark that in as well. Right there. We'll call it M for a bit. We look for our slope. Remind ourselves that it's y2 minus y1 over x2 minus x1, or that's the same as rise over 1. But we're going to still take in these values. Our y2 and x2 is usually the rightmost point. So we're going to take q because it is our rightmost point. We're going to say 1 minus 3 over x2 is 4 minus a negative 2. Now, of course, a negative minus here is going to be positive, positive. That double negative will change it. We will then get negative 2 over 6, which will reduce down to negative 1/3. But remember, we're looking for the equation of the perpendicular bisector. I don't want the equation for the original. I want the perpendicular bisector. So if we think back, perpendicular means to take the opposite reciprocal. So we are going to take this value, negative 1 over 3. We're going to change the sign to make it a positive. And we're going to flip the fraction to make it a 3. And this is the perpendicular slope that we would be looking for. Positive 3. And from here, I recommend putting it into point slope form. However, it is possible to find mx plus b, the slope intercept form, but that's just me. And so with point slope form, it's y minus y1, and the y1 actually comes from that midpoint that we found. So y1 is 2 equals taking our 3, our slope, and putting it into the equation, 3 times x minus 1. And because it doesn't specify how to find find which equation, we can just stop right there. But if you do want to change this and put it into y equals mx plus b, here's how we're going to do it. First, distribute the 3 over. Y minus 2 equals 3x minus 3. And add the 2 on both sides, essentially just solving for y. And that's our answer. Again, I would move on to the next example. I would wait until watching, or I would wait from watching the rest of this video. I would rather you solve it on your own at first if you can, and then we can come back and you can see how to solve the problem. But just in the interest of time, I'll go ahead and give you the values as appropriate. So the midpoint should have been negative 3, 1. The slope you should have found. The slope you should have found for the original line should have been negative 1 over 4. But then the perpendicular slope should have found to be 4. And the equation you should have gotten is y minus 1 equals 4 times x. Now here is where it gets a little bit tricky. We do have a negative sign here, or minus sign here. But because we have a negative x value, we're going to put those in some parentheses. But recognize that this simplified is going to be x plus 3 in the parentheses because of that double negative. And again, if you wanted that y equals mx plus b, it's going to be y equals 4x plus 13. And that, ladies and gentlemen, is the conclusion of this lesson.